Let's do the fundamental example of finding variance by conditioning. You've known for some time how to find expectation by conditioning, and now we are going to find variance in the same way using our new formula. The variance of a random variable is the expectation of the conditional variance plus the variance of the conditional expectation. Let us see what this means in a particular context. So I'm going to start with two random variables, y1 and y2. And let's have some notation for their means and variances. So the means I'm going to denote by mu, and the variances I'm going to denote by sigma squared, indexed by the random variable. And now we're going to define a new random variable, which is one of these chosen by the toss of a coin, except it's now a biased coin. And we define a new random variable y based on whether the coin is a head or a tail. If it's a head, y is y1, and if it's a tail, y is y2. This move, creating a random variable by conditioning in this way, is called mixing. Y is 1 of y1 and y2. You just don't know which one. It's a random one. And this move is called creating a mixture. So we'll say the distribution of y is a mixture of the two distributions, or y is a mixture of the two random variables. Okay, so we are going to find the expectation and the variance of y based on what we know about the expectation and variance of the two individual random variables, and of course what we know about the coin. So let's give the coin toss a name. So let x be the indicator of heads. Then let's start writing down some conditional expectations and conditional variances. The expectation of y, given whether or not the coin landed heads, is a random variable, and it has a distribution. And the expectation is something with probability p and something else with the remaining probability q. And so if the coin lands heads, the random variable is y1, and so its expectation is mu1. And if the coin lands tails, the conditional expectation is mu2. Notice how simple that random variable is. It looks more complicated than either y or x, but it is very, very simple. It is merely a two-valued random variable. It has one value for each of the values that of the conditioning random variable. So x has two values, so any function of x is going to have at most two values. And the variance of y given x is similarly a two-valued random variable. If the coin lands heads, your random variable, your choice is y1, and so the corresponding variance is sigma 1 squared and then sigma 2 squared with probability q. Now the expectation is the expectation of the conditional expectation. So so we've got this little distribution table, and that expectation is mu1 times p plus mu2 times q, and expectations don't get much simpler than that. Why don't we just, because we're going to use this later, I'm just going to call this mu. Okay, so now our job is to find the variance of y. And that is going to be, by our formula, the expectation of the conditional variance plus the variance of the conditional expectation. And the conditional expectation we recognize as the distribution that we wrote down first, and the conditional variance has the distribution that we wrote down next. So what is the expectation of the conditional variance? Well, it's a little two-value distribution. Its expectation is sigma 1 squared times p plus sigma 2 squared times q. And now we have to add the variance of that two-value distribution of E of y given x, mu1 with probability p and mu2 with probability q. So what's the variance of that distribution? Well, it's the expected square minus the square of the expectation. The expectation we already found. We've called it mu. So I have a minus mu squared. And now I have the expected square. Well, the values are mu1 and mu2. So the squares of those values are mu1 squared, and we get that with probability p. And then I have a mu2 squared, and we get that with probability q, and we are done. This simple example is a workout in all of the little pieces. It helps you understand that the conditional expectations and variances, far from being complicated, are actually very simple, and that to get the unconditional expectations and variances, we just have to compute E and var of very simple random variables. And we just have to remember how to do that from way back when.